In this video, we're going to look at one of the underpinnings of improper integrals, and that is, does it even make sense to ask this question? What do we mean when we talk about convergent versus divergent integrals? And there's two intuitions that typically come up. One is, we're integrating out towards infinity, and then we take an area underneath a graph, but this side here, I hate to write this and I'm going to erase it momentarily, but the side length here is an infinite quantity. So how can you do that and not get an infinite quantity back for the area? Well, that's a good question. That's one reasonable critique of this whole process. The counter argument is you're multiplying that infinitely long length by values or heights that somehow involve a height of 0. These graphs all converge towards 0. So there's a bit of a balancing act, but that's not very convincing. We'll find something a little better in a moment. There's another side of the coin, though, which is if we look at the graph is going to 0 no matter what. In fact, it's going to 0 usually pretty quickly. So if we talk about this area, then how can we ever get an infinite area out of this? This graph is going to 0, so it's going to basically cut itself off at some point. It never quite does because it's always an asymptote, but still, how can I get an infinite amount of area tucked in underneath that graph? Both good questions, and both are actually possible in terms of getting infinite or non-infinite finite areas out of these scenarios. Underlying this is the reason why we need to be very careful how we do these integrals and evaluate these integrals, because we're talking about a tension again between infinity and 0, very similar to what we've seen in earlier limit questions. Let's address the two scenarios in the same order. Imagine we're trying to build something that's infinitely long this way, and I want to construct something that has a finite area. Because one of the claims is, well, if one side length is infinitely large, then how can we ever not have an infinite area? How can we ever have a bound on the area underneath that? Well, it's actually not hard to construct an example where we get exactly that. What we're going to do is build a rectangle, and it's going to be 2 high. We're going to build it out of 2 squares, each of length 1. And what we can imagine doing then is taking that same area and then just putting them side by side for a second. I think we all agree that the area in both those cases is 2. We haven't changed anything. What we then do is we're going to segment or cut this one in half, and we will move the top piece beside the one before. So we'll have an area of 1, and then a half, and then a half. Pretty reasonable. Then we're going to do that again for the last block. We'll keep our block of size 1, we'll keep our block of size a half, and then we'll cut this block in half. That will give us 2 blocks each of height 1/4. And the x-axis now stretches out to 5. Each of these have an area 1/4 and 1/4. And you can see the pattern we're going to get here. If we just keep cutting these things in half, we're going to have blocks that are always half as large as the one before it. But there's still an area, still a positive area. But we can do that in an infinite process. But guess what? The area here, even though it's going to stretch out all the way to infinity in terms of the horizontal span, the area is always and will always be 2, because we started with 2 blocks that we just cut in half, cut in half, cut in half, cut in half, and laid them out beside each other. So, looking at this picture here, it's quite easy, I hope, to see that we can have a region that is infinitely long, but so long as we are shrinking the height of our blocks fast enough, we can still have a finite area that's being spanned with that infinite horizontal distance. Now, what about the opposite scenario? If we build these blocks and the blocks are getting smaller and smaller, how is it possible that we ever run out of room, that we end up with an infinite area? Well, again, we can build up a quick scenario with that. Let's start off with a block of size 1. We'll make it nice unit lengths here. And we'll make the next one a half. That's so far the same as the last one. Let's make the next one 1/3 though, and then 1/4. So these blocks are all getting smaller, and then 1/5, and then 1/6. Now what's the total area of that region? All these blocks together. Does it stop somewhere? Do we get an area of 4 no matter what we do? Well, let's give an argument for that. There's an area of 1 plus 1/2. We got that. Then we'll group the next two pieces together. The area there is 1/3 and 1/4. And then we'll leave a bit of space and we'll group the next 4, 1/5, 1/6, 1/7, and 1/8. And then we'll group the next 8 as it turns out, 1/9, 1/10, and by the time we're done, there'll be another power of 2, 1/16. And let's just see the pattern that arises out of doing that. If we have 1/3 and 1/4, I'm guaranteed that that's going to be bigger than 1/4 and 1/4, because 1/4 is smaller, so we're taking something smaller. But 1/4 plus 1/4 is 1/2. So this region here is at least 1/2. Okay. What about these 4? Well, if we have 1/5 plus 1/6, well, they're all bigger than 1/8. That is going to be bigger than 4 times the 1/8. I've got more, these fractions are bigger, and I have 4 terms. Well, that means that collection there is going to be larger than 1/2 as well. What about the next one? Here we have 8 terms, and the smallest one is 1/16. So if we took the low end of each of those expressions, we'd have 1/16. They're all bigger than 1/16. So we're going to have something larger when we add all those 8 up that's larger than, wait, 1/2. And so what we get is this total area is going to be bigger than 1 plus 1/2, first 2, plus another 1/2, plus the next 4 terms are 1/2, plus the next 8 terms are 1/2, plus the next 16 terms, 32 terms. In other words, we can make this as large as we want. If you want to make the total 100, just keep adding enough terms. We have an infinite number of them, so we're never going to run out. But the sum of them is always going to get larger and larger and larger. And so even though all of these values are getting smaller, the heights of them are getting closer to 0, if we add them up and they have this relationship to each other, we can get an infinitely large area if we want. Again, it depends on these particular sizes. If we go back a page and look at this example, the way these blocks change size was getting smaller faster than the last example. And so we end up with a finite area in this case, but here we end up with an infinite area, just by the relationship between the infinite length and how quickly these blocks get smaller. Altogether, that makes this a rich area for study for mathematics when we're interested. Altogether, that makes this an interesting area of study for mathematics because it has or involves the tension between those infinite quantities and these values going to 0. And now we've provided a systematic way to handle that case using our earlier ideas of integrals and limits.